Hello, everyone. My name is Gal Morgenstern, and I'm going to present our joint work with Professor Tirza Routtenberg. We're both from the Ben Gurion University of the Negev, and we're very delighted to be part of this ICASSP conference. So our presentation is going to be in the context of graph signal processing. And if we observe graph signal processing, it is really doing a majestic job on how to redefine filtering, sampling, spectral analysis from problems, from vectors to signals that are spanned over graphs. And we wanted to join this mission. And today we're going to present how to expand the notion of sparse recovery, which is the basis for compressed sensing and group testing, to signals over graphs. So let's go to the slides. So now you get a very small version of me here on the right corner. So our work is called Efficient Recovery of Sparse Graph Signals from Graph Filter Outputs. And we already published an article on this topic in the transaction of signal processing. So there will be a QR code at the end. As we said before, graph signal processing is everywhere. It allows to model and to use tools from signal processing for social network transportation, sensor networks, biology problem, water system, power systems, and etc. And if we consider sparse recovery in these networks or network science, there's a lot of problems such as opinion forming, rumor spreading, finding the source of a disease, finding the source of an anomaly, such in computer networks or power system, or even trying to define a seizure in the brain networks. If we consider more theoretical works, the graph sparse recovery relates to signal reconstruction, blind deconvolution, system identification, sampling, and more. These are only examples. So if we consider the problem of sparse recovery, we have in this context, we have three interesting elements. We have the signal X, which is a sparse signal defined with non-zero elements over the support omega. We have a filter or a dictionary. Depends on how what perspective we look at the problem. And we have observations, and we're trying to find, in this case, both X and omega. And in order to make this problem more interesting and more related to graphs, we have several assumptions that we're going to use. One is that the filter is a graph filter, and we're going to touch this later. And the second, we have some more assumptions on the graph. In this case, that the maximal nodal degree is small or not too big. And instead of looking on the sparse recovery problem, we solved the least square problem in the inner minimization problem and fix this a bit. And then we can use the support recovery problem, which in this case, we try to find which omega maximizes the projection of y over the column space of h omega. And the other part is a penalty function defined based on the GAC, and I'm not going to delve into this too much. So talking about our assumptions, so this is a problem we're going to solve, and we're going to solve it based on two assumptions. The first assumption that we're considering graph filters. And the main thing, I'm not going to talk too much on graph filters, but the main intuition I want to provide here is that if we have, based on the filter degree, is the influence of the filter. And I'll give an example. If we have a signal defined only over node 2, then the non-zero elements of the filtered signal, if the filter degree is 1, will be only in the first order neighborhood of that node. If it will be a filter degree of 2, we can see that the elements will be in the second order neighborhood. So this is the main concept we're going to use, and we're going to explain how to use it in a moment. So the idea here is that given that property, we can define an orthogonality property associating between the dictionary atoms to their indexes, which are associated to nodes over the graph. So in this case, we can see that if we consider nodes that are close to each other, L1 and L9, then the dictionary atoms L1 and L9 will have similar measurement spaces, so they won't be orthogonal. But if the distance is far enough, in this case, we consider a first order graph filter, and you can see that 1 and 7 are not too close, then the measurement spaces will be of different measurements. And in this case, they will be orthogonal. So generalizing this concept, we get that the dictionary atom HK and HM are orthogonal if K and M over the graph are bigger. The distance between K and M over the graph is bigger than 2 psi. So this is the main property we're going to use. And to make this effective, we need to consider something about the graph, because if we consider a high maximal nodal degree, in this case, the complete graph, all the nodes are neighbors. So this orthogonal property doesn't give us a lot. But if we consider a low maximal nodal degree, which makes more sense with real life applications as well, then this property makes a lot of sense. Hence, in this case, this node and this node could be distance over the graph. They're pretty much far away. And this forces a double sparsity, because the low maximal degree also forces a sparse graph shift operator, in this case, the graph Laplacian. And if we consider in this example, we consider a first order graph filter with the sparse element X, and then we get that some of the observations are 0. And this is very important to what we're gonna show in the following. And we can use this because we want to, at the end, we want to solve the GAC problem. So one thing we want to know is which measurement spaces are affected by the filtered signal. So we can project the filtered signal over the column spaces HM for each M nodes. And basically this will equal 0 if M is not in the second psi order neighborhood of omega. And in easier words, if the distance between M and any element in omega is bigger than 2 psi. In this case, you can see that the measurement spaces between the dictionary atom 7 and PL1 are define different areas in the measurements, and therefore they're orthogonal. So this is the main property theorem we're going to use. And this goes straight forward from the property we had before. So, and another interesting part of this is that because of this theorem, and now if we consider Y, which also includes noise and the filtered signal, then the projection of Y over HM will contain only noise if M is not in the 2 psi neighborhood of omega. And to make things even more interesting, and we're not going to talk about this too much, the 2 psi order neighborhood of omega can be bounded. And it's bounded based on the characteristics of the sparsity of the signal, as well as the graph, the maximal nodal degree, and the filter degree. So what you don't see here is that it's not influenced by the size of the model. So for very big, so the size of the model of the graph doesn't influence the size of the 2 psi order neighborhood. So this is a very big thing, and this is not a tight bound. So this could be even less, even smaller. And we even want to add a bit more control. We want to show, we define the set D that includes, it's a subset of the 2 psi order neighborhood of omega t, and it includes only elements with meaningful information on, on the filtered signal. So that's pretty much it. And now we did 3 methods, but we don't have a lot of time today. So I'm going to present the first method more thoroughly, and then briefly I'm going to present the 2 other methods. And then I'm going to show some experiments. So the idea here in the GMGAC is to first identify the candidate set and then to partition it. And I'm going to talk about this in a moment. And after this partition, we can do local GACs, which are extensive, but they are in a very small area. So that's not too bad. So this is the idea. So to identify the candidate set, we're pretty much relying on the idea that on one hypothesis we have only noise, and the second hypothesis we have signal and noise, and then we can use the GLRT, and then to estimate if each node is associated to a meaningful information or just to noise, and that's our D hat. So that's the first part, and then we can try and do partitioning if the areas, if the elements could be distant enough, if I can find 2 sets such that each element is larger than 2 psi, so I can separate them because I know that the dictionary atoms in each one of them will be orthogonal. And that's what we get here. So that's the idea. And after I separate them to orthogonal spaces, I can perform local GAC within each subset and then just use all the results combined. That's the idea. So this is the first method. The second method tries to do something similar but iterative. Because the first method is a lot faster than the GAC, but it's not as fast as the OMP or lasso or other sparse recovery techniques. And the idea here is that we're trying to define this as a branch and bound problem. So we first restate this as an integer programming problem that we can split into two subproblems. So by using this split, we can define a decision tree, and where each subproblem can be defined by what you see on the right. Basically, we have S0 and S1, in which elements are included or excluded from the support. So, and for each subproblem, we can define bounds. So the difference between our method and basic branch and bound is that we use all the analysis we had. We use this in how we define the upper bound, and we use this in how we choose which node in the decision tree to split. And in addition, we use this in order to define how to split it, which index to define as 1 and 0. And if you want further information, you can go to our article. Another method is the GFOC, which is very, very simple. The idea here is that we use a different sparse recovery method. This is a correction method. So we consider an input of the support, of an estimated support, and then we ask a question for each element in the support. And the question is simple: if we replace this by one of its neighbor, do we get a better result compared with a cost function? And if the answer is yes, we switch this, and we do this iteratively on each element on omega. So a bit of experiments. So in our article, you'll find very complicated experiments on stochastic block models, how to integrate our method with blind identification and to estimate brain signals, and even how to use our method to detect the source of a cholera disease. Here, I'm going to present something very simple on the square grid. So in this case, the support is in the center of the square grid, and we are showing the F-score accuracy of the support estimation over the graph filter degree. And we have the lasso method and the OMP, which are pretty basic, and you can see that they have different results. And we even show the L1 BNB. And a very interesting thing about the OMP is that the OMP-C is the correction, the GFOC correction of the OMP, and you can see a vast improvement only by the GFOC, only by the correction we showed earlier. And then we have our methods, which show on the higher graph filter degree, this is the iterative method, are much higher. And when using the GFOC, they're even comparative in the lower degrees and much higher in the higher degrees. And then you have the GMGAC, which, as I said, is very close to the optimal GAC solution. And the second thing I want to show here is that given runtime, we operate a lot faster than the GAC. And I don't have a lot of time, so I'm going to show this pretty quick. You can see that GBNB is not too far from the OMP and the lasso. And then you can see the GMGAC, which doesn't change with the size of the model. The size of the model is tier X. And you can see that the GAC changes and grows exponentially with the size of the model. And I want to say thank you for listening. This was a great talk. I hope I didn't speak too quick. And I hope you all get a chance to see our journal article. It was great seeing you. Thank you. Have a great conference. Have a great time in India. And goodbye.